Welcome to falling objects. So before we get into the differential equations, let's just do a little physics background. And the differential equations will fall out of that. So an object falling close to Earth experiences two forces as a general rule. So we have our object. It will experience a downward force due to gravity, which I will just label as F sub G. And this is negative mg, where m is mass in kilograms, and g is 9.8 meters per second squared. The negative is because I'm taking downward to be the negative direction. So the force due to gravity should wind up being negative m times 9.8. In the opposite direction, we have the force due to air resistance, which I will shorthand F sub A. And this is equal to negative K times V. Here, K is what is called the drag coefficient. The drag coefficient depends on the object falling and the form that it's in. And V is velocity. Now, from physics, we have total force. Is F is equal to the sum of the forces acting on the object. So this should be equal to F sub A plus F sub G. We also have the total force as mass times acceleration, or mass times the derivative of velocity with respect to time. So this formula gives us mass times the derivative of velocity is equal to negative kV, there's our force due to air resistance, minus m times g. So we have a differential equation that fell out of our various forces acting on our object. So now let's work with some specific numbers. Let's suppose an object with mass 5 kilograms is dropped off a 600-meter tall skyscraper with initial velocity 0 meters per second. The object is known to have a drag coefficient of 0.5, and the acceleration due to gravity is 9.8 meters per second. The first thing we want to do is write the IVP. So the information we need, we have our initial velocity of 0 meters per second. We have a mass of 5 kilograms. We have a drag coefficient of 0.5, and the acceleration due to gravity we already had set, but that is that 9.8 we spoke about. So again, here we have mass is 5 kilograms. We have our drag coefficient is 0.5. G is 9.8. And we have V of 0 is 0. So we can go ahead and plug into our differential equation. We have m times V prime is negative kV minus m times g. So 5 times V prime is negative 0.5 times V minus 5 times 9.8. If we divide through by that 5, we get V prime is equal to negative 0.1 V minus 9.8. And here we have, again, V of 0 is 0. So here's our IVP that we will be working with for velocity So now we want to solve that IVP. This is a non-homogeneous linear differential equation. It is also separable. Personally, I think it's fastest to solve it via just finding the homogeneous solution and then variation of parameters, but it is up to you whether you want to do separable or that route. So we have V prime plus 0.1 V is equal to negative 9.8. Initial condition, V of 0 equals 0. You can first find the homogeneous solution. We know that V1 should be e to the negative integral of 0.1 dt. So we get that our V1 is e to the negative 0.1 t. From there, we run variation of parameters. We will assume V is equal to some U times V1. I need to pause and reset my screen. From there, we know that U prime should satisfy the right side of our differential equation, negative 9.8 divided by our V1. So our V1 was e to the negative 0.1 t. Reworking this becomes U prime is equal to negative 9.8 times e to the positive 0.1 t. If we integrate, we get that U is equal to the integral of negative 9.8 e to the 0.1 t dt. U is therefore equal to negative 9.8 divided by 0.1 is negative 98 e to the 0.1 t plus c. We then have the V of t is V1 times U. So we have e to the negative 0.1 t times negative 98 e to the 0.1 t plus c. This becomes negative 98 plus c e to the negative 0.1 t. If we then use the fact that V of 0 equals 0, this means that c has to equal 98. And we get, let me give myself a little more room again. I apologize. We get then that V of t is negative 98 plus 98 e to the negative 0.1 t. Now from here, let's write an IVP to model height above ground t seconds after release. So V is just the derivative of height, essentially, displacement from the ground. So note, if h of t is height above ground, then we have V, velocity, is just dh dt, or h prime. So we have the equation we had previously, just gives us h prime is equal to negative 98 plus 98 e to the negative 0.1t. And then we were told at the beginning of this problem that the height of the building that it was dropped off of was 600 meters. And so this again is dropped from 600-meter tall building. So the equation for velocity itself is a differential equation about height in this case. So if we want to solve the IVP, we can just integrate. And we get that h of t is simply the integral of negative 98 plus 98 e to the negative 0.1 t dt. Taking this integral, we have negative 98t. Then we would have plus 98 divided by negative 0.1 becomes minus 980 e to the negative 0.1 t plus c. Then using the fact that h of 0 equals 600, this will be negative 98 times 0 minus 980 plus c is equal to 600. That gives us that our c should be equal to 1580, 1580. And so we have the equation h of t is equal to negative 98t minus 980 e to the negative 0.1 t plus 1580. Next question, how many seconds will it take for the object to reach the ground? We want t such that h of t equals 0. So we're looking at 0 is equal to negative 98t minus 980 e to the negative 0.1 t plus 1580. This is not an equation that I can easily solve by hand. I'm just going to go ahead and use technology to do this. So I'm going to use technology. And find where this equation crosses the x-axis if we set h or y equal to what's on the right. So I'm going to pause and switch over to technology, and then I'll show you what I get. Well, here I'm using an online graphing calculator, Desmos, and I typed in the equation using y and x instead of the variables we started with. I had y equals negative 98x minus 980 e to the negative 0.1x plus 1580. Desmos graphed this for me, and then it automatically calculates the intercepts for you to the best of its ability using a numerical approximation technique. And in this case, it's showing that that x-intercept is 13.541. So we get 13.541 or approximately 13.5 seconds. Again, here's what we just did in Desmos. I just changed the variables. X is acting like my t. Y is my h of t. And so here, when t is approximately 13.5, h of t equals 0. So we have the object will hit the ground approximately 13.5 seconds after release. So adding in this drag coefficient complicates the formula for a falling object. It's no longer that sort of basic 9.8 over 2 or negative 9.8 over 2 t squared plus your initial velocity times t plus your initial height. We now have a slight variation to that due to this counter force we're working with.